Echo. How about now? Thank you for that, because I would have gone on the entire time muted. What is this? What is going on here? Oh, here we go. Did you notice what I gave you? What are the values of those little resistors? Yeah. How do you know that? How do you know that? Because Kyle told you. Yeah. What is it? Brown, black, brown? It's 100 ohms.
It was big boys race our young girls, but violet usually wins. I think it was like that. I don't remember. It was like color code thing. I was trying to remember what the name was.
Let's make up one. Brown is what? Where does it go? Brown what? What?
It goes. It was black, brown.
Black, brown,
red,
girls, big.
Wait, what?
What did you say?
It's kind of a thing that we have the name for the select.
I know what you're talking about. I just never memorized that. Was that something that like?
It was big boys race our young girls, but violet truly wins. I don't know.
That is kind of creepy.
It was something like that. No, it's violet generally wins. Because generally is gray and wins is white. So it's a big thing.
All right.
So
Well, anyway, what I gave you is 300 ohm resistors, but they look a little different, right? So the smallest one is 100 ohm. How many watts do you think it is? Small, quarter watt. The little bit bigger one is 100 ohm, half watt. What's up?
You haven't heard anything about the bookstore's meters for these guys, have you?
I haven't yet.
Should I tell them to just check with the bookstore in the backlogs, or how?
Yeah, tell them to call the bookstore. I'll try to call them again too.
All right.
Sorry.
I figured they just gave them a story.
Yeah.
Yeah, we'll get them to you.
I'm sure they got a giant cluster going on with everybody trying to get their books remotely and everything. So, all right. And then what is the other one? 5 of them. Five watts. So what is the power formula?
our formula, that is, it was,
Right. It's the easiest one to remember because it's the word pi. Power equals current times voltage.
I never noticed that.
So if we have a circuit in here with a DC power source, with all 3 of these resistors, we could figure out with a given current what voltage we could put across these resistors. So is this a series circuit or a parallel circuit? Series. I don't know if have you gotten into that in class yet? Right. In person or in person, end to end. The current will flow through all of these equally. So in a series circuit, given a voltage, the voltage is going to drop across each resistor depending on those resistive values, but it's good because we have the same values. So it's going to drop equally. So if this was 3 volts, what would this resistor have across it from here if you put your voltmeter on it? This is stuff that you guys haven't gotten into in class yet, but we need to understand it for this little experiment.
It'd be 3 volts if we don't know.
Well, this is 100 ohms. This is 100 ohms. And this is 100 ohms. Since they're even amounts, the voltage is going to drop evenly across there. So think of it this way. If current is flowing this way in this circuit, when the current gets to this resistor, it's got maximum potential. There's 3 volts here ready to be used. So we're going to drop evenly across each resistor, which means this thing's going to eat up 1 volt. Right. It's not that you don't have anything left. It's that the potential of difference is all used up. Okay. In any series circuit, whether you've got 2 resistors, it's 1 ohm and then 1,000,000 ohms. The 1 ohm resistor is going to eat up a lot because it has less resistance. Right. Does that make sense? So anyway, this is later on down the road stuff, but since they're even amount of resistance, they're going to eat up the same amount of voltage. That's important because we want to see what happens to each resistor with more current. Okay, so each one of these is going to eat up the same amount of voltage. So this is going to be 1 volt, and this is going to be 1 volt if we put 3 volts across there. So what would the current be in this circuit? In a series circuit, the current stays the same throughout the entire circuit. Also in a series circuit, the resistance is additive. So what would total resistance be in this circuit? 300 ohms. And what would total current be? So E total, 3 volts, I total, oh, excuse me, that's R total. What would current be? Total current. This is Ohm's law, so I equals
It'd be 10 million.
I equals E over R, right?
Voltage divided by resistance.
So total would be 3 divided by 300. So it would be point 0.01, wait a minute, 0.1? 0.1, right? 0.1 amps. 3 divided by 300 would be like 1 over 100. So 0.01, 1/100th. My brain is smoked. Okay, so 0.01 amps. Knowing these values, can these resistors handle that? So we know at this resistor, there's going to be 100 ohms, 1 volt, 0.01 amps. 100 ohm, 1 volt, 0.01 amps. So what is the power going to be used up by those resistors? P equals I times E. So it'd be 0.01 times 1, right? So it'd be 0.01 watts for all of these. Is this making sense? Am I losing you? All right. If we set up this circuit, we know that we would not burn up any of those resistors because the smallest resistor value, the tiny little resistor, can handle up to 0.25 watts, right? You see where I'm getting with this? So then what happens if we start bumping the voltage up? Current starts to go up. Current is the enemy. Current is heat. And these things actually, even though they don't do anything fun, you know, we're not seeing any lights turn on or motors spin or anything, they're using power. It dissipates power in the form of heat, right? So eventually, if we start bumping up the voltage, the smallest one's going to burn up, right? So let's hook up this circuit first, just how I have it drawn up, 3 volts, and put your multimeter in series with the circuit, just how I have it here, so we can read current. You understand what I mean? We had the same type of setup the other day with our meter in series with the circuit, right? I'm going to set it up on my proto board so that you can see how I have it set up. And if you have any issues with creating this circuit on your proto board, let me know. Kyle, you weren't here the other day, so you probably need some wire, huh?
Yeah.
Fine.
Oh, no, actually, I got some.
You got some?
Yep, I got some. Have a good one.
Also, there's gloves, sanitizer, ICC face masks for you if you guys want
Big face mask. Wow. Oh, not yet. I don't know if he wants. Usually if it's never away from my door.
to. I never did that for you. You're set up? What are you reading for amps? Well, you should be on your meter though. You should be reading current. Remember, we got to move the leads down to here. To read current. We're going to read DC. current. All three. Listen, we're going to put all three of them in the series. Doesn't matter, however you want to do it. You get the power in this. You get the power. Power to. Yeah. Power to produce power. All that crap. All right, so here's how I have mine set up. the first thing I want to do is draw the circuit. This is basically what we're doing, right? This is just the same thing I just wrote up. And then I'm going to put a meter measuring current right there. So we know that what we're providing here, E total, is 3 volts. What is our R total? Resistance total?
Maybe 100. My bad.
Series circuit, it's additive. So you've got 300 ohm resistors. So what's the total resistance? 300 ohms. And just like on our last lab, I'm going to measure total resistance. So on my meter, on my meter, I've got my little mini grabbers. And this one, because this one says ohms, and this one is the common for that. And I'm going to measure on my circuit total resistance by measuring end to end. And I should get about 300 ohms. So I need to set this to ohms. 0.297 kilo ohms. So I'm going to write that down as 297.43 ohms. So at 3 volts, (3 volts, 297.43 ohms, what should my current be? I equals E over R. So my current total should be 3 divided by 297.43, which equals 10 milliamps, 10.09 milliamps, or I'll just keep all the units the same, 0.0101 amps. Now with this circuit, I need to put 3 volts from end to end, but I also need to have my meter in there reading current, correct?
Correct.
So what I'm going to do is I'm going to take, I really need to get some tape and color these ends so you can tell when you look at this what is what. But this is my power supply. So this is plus 3 volts. By the way, if you start getting your little mini grabbers popping off of your wire, you see how the little hook on the end is kind of bent out off. If you take your strippers or something, or even probably your fingernails, and just kind of cinch that thing back around a little bit, so it's in more of a hook shape, it'll stop doing that. So here's plus 3 volts, and I haven't turned my power supply on yet. But instead of going back to the source, to the power supply with this, I'm going to put it through my meter. So this is going to be my ammeter, positive, and then I'm going to take the negative of the power supply of the meter and hook it right to the negative of the power supply. So I'm just going to hook these two end to end, and this will complete the circuit. Make sense? Yes, no, maybe so? So, on my meter, what do I need to do to read current? Well, first thing I need to do is take the red lead and move it down to here to read current, right? And then I need to go shift to DC current. Right now we're reading basically 0. My power supply, I'll turn that on. And I want to put 3 volts on it. When I turn channel 1 on, I should see 10.1 milliamps, hopefully. Did you get it?
Yeah, I got it. Did you turn your amperage up?
Yep. 10.03. 10.03 milliamps. Eh? Pretty cool, right? Ohm's law works again. Everybody getting that same reading? Milliamps? What was your total resistance?
Well, his channel turned red, which means wrong.
So what, if we have 100 ohm resistor with a 12 amp on it, so that's 5%, what are they allowed to give us? 100 ohms, they can give us 95 to 105 volts. Everybody else get my same reading? No? Huh. Huh. You're reading 66 on the power supply there. Okay. So which one is your power supply? It's okay, those will be fine. So we want to go plus 3 volts. This one. And on this side, we want to take, we want to put the meter here, so it's your positive meter. Now we put 2 volts on. You want to complete the circuit. The other side of your meter will extend that to the power line for this. This year, you know, so that. We want to read. Because they allow more. Yeah, that's why you got a little bit more current flowing through. I mean, we're talking milliamps, very, very small amount. Yeah. That's just the difference in the resistors. So now let's figure out, what do we need to do to burn up a 1/4 watt resistor?
Increase the peak voltage, I'm guessing.
Increase the voltage. So if we went to, Let's get our whiteboard out again.
I know, but still for that, if I actually.
If we increase the voltage, is that going to do anything to the total resistance?
No.
No, the resistance is a fixed value. So, if we know that power is I times E, and we're trying to destroy our quarter watt resistor, 0.25 watts. So P equals I times E. What current and what voltage do we need? 0.25 watts. Total resistance is 300. Do you have a formula on your ohms, your uglies book involving power,
Yeah,
resistance, and voltage? P, R, and E?
it'd be E squared divided by R.
E squared divided by R. So 0.25 watts is E squared divided by 100 ohms.
Yes.
What voltage could this quarter watt resistor handle? So E squared equals 100 times 0.25. E squared equals 25. E equals 5. So we can put 5 volts across this thing, up to 5 volts across this thing, right? So if this is our quarter watt resistor, right here, we can put 5 volts across it. How do we go about putting 5 volts across it? Just turn your power supply on 5 volts. If you turn a power supply on to 5 volts, you're not going to have 5 volts across this resistor, right? Because the voltage is going to be spread evenly across all 3 resistors. They're the same value, right? So what voltage do we need to have to produce 5 volts across that resistor? There's 3 of them. There's 3 of them. So whatever voltage you put on that circuit, it's going to dissipate in 3 parts evenly. So if we want 5 here, we need 5 there and 5 there. So we need 15, right? The last thing we need to check is how much current is that going to be? If we put 15 volts, I know this is probably confusing, but hang on. If we put 15 volts on here and there's 300 ohms of resistance, how much current is that? I equals E over R, so 15 divided by 300. Correct. So 5 milliamps, which is okay. The reason you want to check that is your power supply is only gonna output, I don't know what this one's rated for, a certain amount of current, which is why I brought this thing, because this thing can handle a lot, right? But your power supply should be sufficient to make some smoke. 3 amps, right? So we're okay to use this power supply to blow up our really small resistor. Now, in order to be OSHA friendly, and so I don't lose my job, can we put some safety glasses on? You guys are excited, aren't you? All right, so if we think that we put 15 volts on this circuit, our smallest resistor will burn up. It might not happen right at 15 volts, okay? So I'm just gonna start creeping on my voltage, and you guys can watch mine first to see what happens to my resistor before you do it. It might not happen right at 15 volts. It might not happen when you put 5 volts across that smallest resistor. What 5 or a quarter watt is what that resistor is rated for, right? So if your car is rated to only go to 90 miles an hour, do you think you could go to 150 miles an hour and it'd still be okay? Maybe, just not for a really long amount of time, right? So we might have to go over 15 volts to actually get it to burn up, but you will see. And if you want to touch the resistor, you can to see how hot it's getting. 15 volts DC is not going to hurt you. Okay, just don't put your tongue on it. Okay, so I'll do mine first, and we'll try to see if we can watch that. What current is that? 0.005 amps. 0.05 amps. 15 divided by 300. Okay, so 50 milliamps. So about the time we see, let me switch camera. I'm going to start. Get this thing up higher so you can see it. I'm going to start bumping up the voltage. So you'll see this thing climb eventually to 15 volts, I hope. And you'll see this thing start to climb up to half an amp or 50 milliamps. Somewhere around that 50 milliamp mark, we should see the smallest resistor start to smoke, turn black, and all that fun stuff. Maybe if we're lucky, it'll explode, and I'll get something in my eye because I don't have my safety. Shh, Brett, I'm recording. Okay, now that I have my safety glasses on, I'll start bumping. Oh, that's current. See the milliamps going up? Ooh. Are you excited? Watch this be a total failure and nothing happens. All right.
It's like that one little next, you're like, oh, it's gonna happen. Nope, not gonna happen.
So now we're at 6 volts and 20 milliamps. We need to get up to 15 volts and 50 milliamps. And I'm at 10 volts, 30 milliamps. Not really getting very hot yet. Isn't that kind of cool that our math is working out too? As we approach 15 volts, we're approaching 50 milliamps. I'm kind of a nerd, so that stuff excites me. I don't know about you guys, but all right, 14 volts, 46 milliamps. So we're starting to approach the threshold of what this little guy can handle, right? It's starting to get, oh yeah, it's getting hot. All right, here we go. All right, this is there now. The manufacturer is saying, hey, it's all this thing can handle, right? We're at a quarter watt. Don't go any higher. Let's go higher. 16 volts, 53 milliamps. Getting pretty hot. $17 volts. $19 volts. So being this much over the power rating of this resistor, it's not burning up yet, but you know that if you left this in a circuit that was using this much current all the time, eventually it would burn up, right? But I don't want to wait. I want to see it smoke.
Probably listen to Eye of the Tiger like
All right, 24 volts, 80 milliamps. A strong little resistor.
I said, it's Rocky Beat.
I'll be really disappointed if we can't make this thing smoke. I mean, it's going to smoke. If we have to go to extreme measures, we'll make it smoke. Good grief.
I'm sure on some Rocky music for this thing. Let's go up.
32 volts is all we can do.
Turn up the million.
So what do we need to do in order to put more current through it? Remove more resistance from the circuit. So I'm going to turn this back down.
Oh, let's just give you a little shock.
I'm going to take this big guy out of the circuit. This guy's actually even getting warm. I took the big one out. I'm going to complete the circuit with this guy. Ooh, jumper in here. Actually, I can just move this over here. Okay, going up. So now all we have is 200 total ohms. Damn it.
Oh, there's.
Oh yeah. Oh yeah. Isn't that exciting? All right, so it's holding though. We're holding current. If you can see, we're holding current. So we're at 164 milliamps. So it's burning up, but it's still holding its resistive value. The smell of burnt electronics. And that actually is what I want you guys to smell with this lab. I'm going to try the same thing so you don't have to put such a high voltage on it in order to get it to burn up. I'm going to do the same. I'm going to start over and only use the 1 quarter watt resistor in that circuit and see what voltage I need to give that circuit. I can't believe that thing is still cooking. Even the half watt resistor is starting to burn up a little bit. I don't know you. I don't know if you can see that. $166 milliamps, it's going up. So the bad thing is it's not just opening the circuit, it's making the circuit less and less resistive. Eventually I would blow a fuse in my power supply if I kept this up. But I do want to zoom in on this resistor. Can you see that that half watt resistor is starting to burn up too? All right. All right. Hold your horses. Now I'm going to put just the quarter watt resistor in there. I'm going to do this. Okay, so same setup, just with the 1 resistor. Just start at 3 volts. How many milliamps would we get to? Like 150 before it started to burn up? So I don't know if you can see. Now I'm on this quarter watt resistor. Keep going up with the volts. I'm at 6 volts. 10 volts. Volts. 15 volts. It already stopped. Like, you see how the current's not going up anymore as I go up with the voltage? It's just staying at 98 milliamps. Do you see that? So that means this resistor's already failed. Oh shit, that's hot. All right, so you guys, if you want to keep the same setup you do have and go all the way up to the max voltage of your power supply at 32 volts, you can do that. Just be careful. You're not going to get hurt by it because the power supply is not going to pump a lot of current through you if you should happen to touch something. But also, if you want to just take that one resistor into its own separate circuit and bump it up to whatever, I think I got up to like 12 volts before that thing failed. Totally up to you, whatever you're comfortable with. I do want you to burn up a resistor because I want you to know what that smells like, right? In all seriousness, it's good to be able to use your senses while you're troubleshooting something. I'm gonna do this again.
Oh, jeez.
What'd you do?
On fire. On fire. Well, guys, you want to see a crisp resistor? This one's open.
Success?
Yeah, it's actually totally black.
You get that all fun. Did you go up to?
Oh, I want the max amperage and voltage. I don't think they're I don't think so either.
Anybody else is burning that? Can you smell that?
Can you smell this?
Yeah.
God, I don't even want to touch that. I don't know how bad that was.
In reality, you can smell that and not see it burn up. You're trying to troubleshoot something. Like you saw that that's half what resistor that I had went bad, but it
this lap and we'll start over. Just be warned, there is smoke in this.
Oh, Gavin, success.
So went firing success. That's almost like you guys. He wants to burn both resistors or keep both of them alive.
We're gonna throw them all away.
Okay, sounds good.
I don't care what you do, as long as you're safe.
As long as I back away and don't light myself on fire.
Oh, by the way, we should probably all know the fire extinguisher is right over here by the door.
Okay, I'm gonna back up for this one.
So while you guys are screwing around with that, I wanted to do one more demo. Light bulbs.
And then blow up the light bulb.
No, we're not going to destroy them. This will only work with incandescents, measuring resistance across light bulbs. But without looking at these, and just taking resistance measurements, I could probably tell some of these are different values than others, right? So if I compared resistance values to this one, this one, this one, this one, I actually put this together as part of the test for my 111 class. Good grief, let's not go too crazy so the smoke detectors go off.
There. There you go.
See, I did.
Nice work, fire.
All right. I should open up the window or something.
Yeah.
Okay, so wouldn't that be great if the sprinklers went off and she ruined all this? Let's take a break from blowing up our resistors for a few minutes and let the smoke clear out. All right. Kind of want to do this so you can also see my meter. Oh. Say hi, Tegan. You're on YouTube. What's up? Stinks, doesn't it? You else getting a headache?
I almost started 2 fires.
I finished my breakfast. Okay. I need some mini grabbers. All right, so if I have a 60 watt incandescent, 100 watt, and let's say 150 watt, which one would have the least amount of resistance? Hmm? $60 watt, 100 watt, 150 watt. Pretty common wattages for incandescent, although you're starting to not see as many of those anymore because of LED lamps. But LEDs, you cannot do this because you're not just going to get a tungsten filament going across two leads. And the tungsten filament in here is going to heat up to the point where it's giving off light, right? That's how incandescent light works. Can you read my meter? Or no? All right. Let's check some resistance here. Somebody write these down so I don't have to do any work. I'm lazy. Light bulb number 1. Jumpy. 33.3 ohms. I have to get it to 4 ohms. So I guess we're going right to left. Write it down. Thank you. Light bulb number 1, 33.3 ohms. Light bulb number 2. 6.9 ohms. Light bulb number 3. 13.7 ohms. Bulb number 4. Uh-oh. Oh well. This light bulb's burnt out. That's the point. There's infinite resistance here because there's a gap in the film. Right? This one burnt out. You ever like shake my light bulb to see if it's because pieces of that film that are rattling around. So light bulb number 4 is out. So we have those 3 values. What were they again? Read them to me. 33.3, 6.9, 13.7. So most, least, middle. Least resistance. Most resistance. So if this was 60, 100, and 120, what do you think watts? What do you think they'd be? Which one do you think would be which? Least amount of resistance, what do you think that was? 60, 100, or 150? It's actually the least. So this would be, what is it? 33 ohms? It would be the least amount of watts. There's more resistance here, giving off less lumens, so it's using less power, right? This one has less resistance, so it's giving off more light and consuming more power. Does that make sense? And then this one. So a couple things that I wanted to demonstrate. One, Ohm's law. So if we're guessing this is 150, I could take the tape off, but I want to play around with it because I'm weird. If we're guessing this is 150 watts, and I put 120 volts on it, how much current should we get here? That's what I want to know. Because I'm doing it. So we're guessing it's 150 watts. We're going to put 120 volts on it. And what would the current be? E equals I times E. I equals P over E. So if we're guessing it's 150, it should be 120 volts, that's what we get out of an outlet, right? Everybody knows that, 120 volts AC. 150 divided by 120, anybody got a calculator? 1.25 amps. Let's see if we can do it. If you ever see me go down, like my heart starts fibrillating or something, and I start like sizzling like a piece of bacon, don't do anything, just go home. I'll be fine. I'll be fine. Just let me cook for a while.
I'll send an email.
Send an email.
Yeah, somebody. Front desk.
Yeah.
A nice dude, email.
So I've got this little used glue here. I'm going to put this thing in series. Now, does it matter with alternating current? Does it matter polarity, whether I put positive on one, negative on the other? It doesn't, because the current's actually going back and forth. It doesn't matter polarity wise. So I need to go, let's say, positive to black, minus to meter. Neutral to negative. Just to show you how I just hooked that up. This is like an AC. This is an AC source. It's like a sine wave. So instead of the battery or the DC source, so I want to the light to my meter, and then back to the AC source. And we're guessing that if that's a 150 watt light bulb, we will see 125 amps. So I'm going to put this on AC amps. We should see this thing light up, and we should see that thing go to 1.25 amps, correct?
Yeah.
Pretty good, right? 1.29 amps. Cool, right?
Sign.
Isn't that cool? Science. Like I feel like Bill Nye the Science Guy, right? You guys ever watch that?
Yeah.
Cool science or whatever. All right, so a couple things that I want to show you is what was the resistance of that lamp?
6.9.
6.9 ohms. Woo, that's getting hot. Duct tape. Duct tape them up. So now that we've heated that filament up a little bit, the resistance of that should have changed a little bit. Do you know if resistance goes up or down with temperature? Some things go higher, some things go lower, so let's check. Let's check resistance. Now that thing's all hot bothered, we should have less than 6.9 or more. Less. 8.5 ohms. Because it heated up, less and less resistance. So that means the copper and tungsten put together, whatever. We'll just pretend it's just a filament, tungsten filament. I'm sure it has other elements in it too. But it has a negative coefficient of temperature, meaning when temperature goes up, the resistance goes down. There are some materials that have a positive coefficient. As it heats up, the resistance becomes more. Right? And those are used for measuring temperature. You know, like we'll get into that here too when we talk about instrumentation and sensors and all that stuff. So anyway, that's my cool demonstration.
I thought it was cool.
Thank you. Got to see some smoke and some fire and some duct tape burnout. So, all right, that's really all I have for today. I hope y'all have a lovely, lovely weekend. I will see you Tuesday, unless we all come down with the Rona. So if you would, your resistors that we smoked or we're trying to smoke, I want to make sure they all get put in the garbage.